I'm a PhD student at Leeds MIT. So I'm going to talk about optimizing information freshness in wireless networks. This joint work with my advisors, Sartaj Karman and Ethan Mariano. So timely exchange of information is sort of gaining increasing relevance with applications such as futuristic applications such as UAV networks, IoT, vehicular networks, where you have to exchange status updates, say vehicles, sharing position and location information, and other control state information. So here's a model to have in mind. So you have a source that generates update packets at a certain rate. It sends it through a resource or a network, and that gets to the destination. Now, if the packet generation rate is too high, then obviously you have network logging, you have delay, and you have a delayed information at the destination. But if the packet generation rate is too low, you have low delay, but the destination gets the updates very infrequently. And so this sort of thing, the delay measure, the conventional delay measure doesn't capture this phenomena, but the new metric, which is called age of information, quantifies this behavior more accurately. And here's this age of information metric was first proposed in Infocom by Sanjeev Kaul, Roy Yates in 2012, and they analyzed a simple FIFO queue. And age is defined as the time since the last received update was generated. So, for example, here's a curve, the age curve. So it grows linearly till you get a new packet, and the time when you get up a new packet, the age drops. And to what does it drop? It drops to the time since that message was generated. So, for example, here the destination gets a message at T1 dash, then it will drop and it sees that this T1 dash message was generated at T1, so the age drops to T1 minus T1 dash. Then it grows linearly again till T2 dash when it gets the next message, and the age will drop to T2 minus T2 dash, and so on. So this is an age curve, and so there are typically two metrics to sort of age. One is called average age, in which we calculate the area under this curve till some time t and divide by t. And the second is peak age. You see this age curve has these peaks before it drops at every reception. So you count the sum of all these peaks and calculates that average. So that's called peak age. So the average age and peak age are two measures of age which are generally analyzed. So what Roy Yates, Sanjeev Kaul in 2012 showed is that there's an optimal input rate lambda at which this age is optimized. So here they've plotted, so in their paper, they plotted age as a function of lambda or service utilization. And for too higher input rate, you have a higher age, and too low an input rate, you also have a higher age because you're updating infrequently, not frequently enough. And there's an optimal lambda at which the age is minimized. So following this work, there was a lot of interest in analyzing age of information for various queues. This is by no means an exhaustive list. There are many more papers, but very few work has been done on wireless networks or analyzing age on wireless networks, and that is sort of the primary reason why age of information is proposed, like analyzing vehicular networks. So here are some 4 works that I know of. So in 2016, Bio, he, Yuan, and Effermentis had a problem of scheduling finitely many packets over a physical interference constraint. And they showed the problem to be NP hard, and then gave some approximate solution. Then the next 3 works typically considered a broadcast channel or a broadcast setting where you could activate only one link at a time, and several policies proposed, but not much work has been done on general interference constraint, and that is what we do in this work. So the resource for us is a wireless network which has all flows in the, so we consider wireless network as single flows, that is every link is a source destination pair, and the resource is constrained by one interference and channel uncertainty. So here's the precise model. You have a network modeled as a graph. Every link in the graph is a source destination pair, um, not all links can be activated simultaneously because of interference. So you have feasible activation set. So for example, in there, either the left set of red links or the right set of red links will be activated, and we call such collection of all these feasible activation set as capital A. So for example, it could be set of matchings in certain graphs, and so on. So we assume time to be slotted, the duration of each slot normalized to infinity, and we have a on-off channel process, which is IID across time, independent across links. It is not identical across links, and gamma E is the probability that channel is on at any given point. Channel E is on at any given point in time. We assume in this work that channel state SC of T is unknown, but I know the characteristics. I know the channel statistic gamma E. So, so this again, so age in our work is because we consider a discrete time setting. So age does not linearly increase, but increase in a stepwise. And the average measure, so average age is given by this expression, which is the sum of the area under that age curve divided by t. And you have peak age for each link, and the network age, what we define it as weighted age for each link, weights being positive. So we assume two kinds of sources. So generally the applications that care about information freshness operate above the transport layer. So what happens is that these applications feed in packets, and these packets get queued at a MAC layer, which has a MAC layer FIFO queue. And that MAC layer FIFO queue cannot be controlled by the transport layer, which cares about the information freshness. So buffered sources sort of model that, where you have a control over input rate, packet generation rate, but you don't. But those packets get queued at a FIFO queue before transmission. And active sources, we consider a scenario where you can actively control MAC or you can generate a new packet whenever transmission opportunity arises. So the control in the buffered source case is a packet generation rate as well as link scheduling, whereas in the active sources case, you just have to worry about link scheduling. And we consider a set of all scheduling policies that decide based on past actions and current and past age. And our goal is to design, as I said, the rate control and scheduling to minimize network age. So let me consider a simple case first, which is active sources. That is, every source has can generate a fresh information whenever transmission opportunity arises. And because it generates fresh information every time, the age curve is simple triangles. So what happens is the age keeps increasing, and whenever you have a transmission opportunity, a fresh information is generated, which is at the red dot, and then the age drops to 1. And then it again increases 1 for each slot, and then again a red dot happens, you have a drop in age to 1. So this is how age evolves in active sources, and you have a natural inequality in which peak age and average age get related. So peak age for any policy pi is less than equal to twice average age minus the sum of link weights. And here's a simple proof how to. So peak age, so if you see this curve, you'll see that the peak age is given by sum of all these SIs, where SI are the interactivation times. And whereas the average age is the area, being the area under this curve, is given by this half of SI, sum of SI square divided by SI. And now you just apply Cauchy-Schwarz inequality and you get the result above. So minimizing over whatever space of policies that you have optimal peak age is less than equal to twice optimal average age. Now this has an important consequence. Very simple inequality, but following is the consequence. Suppose you have a class of policies C, a subclass of your total policy, which are, say, easy to analyze, but have two properties. One is that for any policy in that space C, your peak age is equal to average age. And second, if I minimize over all policies in C for peak age, then it's same as minimizing peak age over all policies. Say if you have these two properties, then what you can say is the policy pi C that I obtain by minimizing over this subclass of policies will be peak edge optimal, that is given in property 2, but it will also be factor 2 average age optimal. And the proof is just one line. So you just notice that by first property, peak age and average age of pi c is the same. By second property, peak age of pi c is optimal peak age, and by the inequality we just proved, it is less than or equal to twice average age. So now, what is a good class C that can satisfy this? So let me just define stationary randomized policy. It's a very simple policy where let B of t be the event that at time t link E was activated. The activation is a decision. So even when I activate a link, my link can fail due to channel uncertainty. So B be that event that link E is activated in time t, and I define stationary randomized policy. Pi is stationary randomized policy if B of t is IID across time. It may not be independent across links. And let Fe be the probability that that event B happens, B of t happens. I call it link activation frequency. So here are two examples. So link E, for example, attempts transmission with probability P in every slot, independent of others. This would be a stationary randomized policy. Another simple one is you have a set of activation sets which do not interfere. So activate activation set M with probability xm. So for example, in this case, you activate the first activation set of red links with x1, the other set of links with x2, and then the link activation frequency is easy to compute. It is sum of xm over all m in which E is a part of. So it turns out these simple stationary randomized policies satisfy my two properties. That peak age is equal to average age for all pi in this class of stationary randomized policies, and I can get minimum peak age by just searching in this simple policy space. The proof is in the paper. I won't discuss it. And here's a result. So for the stationary randomized policy, pi c, which minimizes peak age, can be obtained by solving this minimization problem. It's convex, and I'll tell you what it is, but these are interference constraints, and you minimize some objective. Further, this policy is peak age optimal and factor to average age optimal, which we just saw. So the x's in the optimization problem is nothing but the distribution over collection of all feasible activation sets. So the optimal x that I get by solving this will determine a probability distribution over my activation sets. And here's how my policy will work. So you'll activate activation set M with probability xm star, which is the optimum solution. You can prove a lemma, which is fairly intuitive, that only maximal sets in A would be activated with positive probability.
Maximal means?
Maximal means set is maximal if you cannot add any other element in its belongs. So the complexity of solving this problem depends on network and interference constraints, and this is like studied in literature. But just to give you two examples, suppose you have one interference network, then your set of constraints on F becomes a matching polytope, and then it can be solved in polynomial time using Frank-Wolf algorithm. Suppose you have a K-link activation network where at most K-links can be activated, then the set of Fs become a uniform matroid polytope, and your problem just reduces to this. So the complexity of solving this peak age optimization problem depends on the network interference constraints that we have. But the important thing is we have peak age optimal and factor to average age optimal with just very simple stationary randomized policies. So we're done with active sources. Now let's see what happens in the buffered case, which is the more interesting case, where sources sources generate packet, but it cannot transmit the fresh ones. So the packets are generated and they get queued at a FIFO queue in the MAC layer. Now you can control the generation. Like you can control the rate of generation, the weight, the discipline of generation. It could be Bernoulli, it could be periodic. And the goal is to design, as I said, the rate of packet generation and scheduling policies for age optimality. Now, motivated by our results in active sources, we consider only stationary randomized policies. And I'll give a result as to why that is quite close later on. So, if I'm doing stationary randomized policy, then each queue or each link has a Bernoulli service at rate gamma EFE. So let me just obtain peak age and average age expressions for discrete time G Bernoulli 1 Q, and that was not done before, so we have a result where if you have a FIFO G Bernoulli 1 Q, then the peak age is given by 1 by alpha star plus 1 by lambda, where lambda is the arrival date to the Q, and alpha is the unique solution of this equation. And average age is given by that expression. Lambda is the arrival rate, mu is the service rate, and mx is the moment generating function of the inter-arrival terms. So okay, now let's apply this to Bernoulli periodic packet generation and see what happens. So I'll show just for the Bernoulli case, and I'll give you the results for periodic. So if I just apply for the Bernoulli packet generation, then your peak age and average age are given by this expression, where lambda E is the rate of generation for link E. Now, if you observe the second part, it turns out if I minimize these quantities, then they get minimized roughly at rho E equal to rho is lambda by F, which is your utilization. They get roughly minimized at rho E equal to 0.5. So they're just additive constant of 1. So let me try to ignore them and have this upper bound. And now this upper bound has a nice function to it. So one is it separates into two products. One is 1 by gamma EFE, and this is the scheduling part, and it has the same functional dependence as our function in the active sources had, the one that we're optimizing. So what we can do is we can use the same policy that we used in the active sources case to minimize the upper bound in the buffered sources case. And we can minimize the other part individually. So by this observation, we propose a separation principle policy where you schedule according to pi c, which is a policy that we designed in the active sources case, where the fresh information is always available, and choose rho so as to minimize these quantities, which essentially amounts to saying that I'm designing my rho pretending that there is just a single queue, and I'm designing my scheduling policy by pretending that the sources always generate fresh information. So, and this separation principle policy turns out to be very close to optimal. So the left-hand side is my quantities for separation principle policy, and it's less than equal to the optimal plus sum of weights. And the way to prove is very simple. You just figure out the age at this row that we got, which was an approximate, minus the minimum, and it never exceeds 1 for each link. So over the network, it won't exceed sum of the previous. So you can get similar results for periodic packet generation and Bernoulli for both peak and average case. And so these are the rows that you have to choose. So you choose these rows for packet generation, and you design scheduling as if they were fresh, as in the active sources. In the last table, which is not in the MobiHoc paper but in the archive version of it, we calculate a factor of optimality where you don't necessarily do stationary randomized policy. And we see that for periodic updates, peak age is optimal by a factor of some 2.15, which I think is fairly close. So, numerical results. I'll just give one numerical result. So how costly is the buffer? So I consider the following example. I have n links, at most k of which can be activated. Weights of all links is 1. I have two channels, two kinds of channels, two kinds of links, good links and bad links. Good links have success probability of 0.9, bad links have success probability of 0.1, and theta is the fraction of bad links. And I plot here peak age as a function of k, which is sort of the interference constraint. And so the first observation I see is my, I plotted the red lines are my my separation principal policy, which are my proposed policies. The blue lines are my active sources, and the black dots are the optimal in the buffered case. So I see that my stationary principal policy is very close to the optimal, much closer than what my theorem predicted, and there is a cost of there's a significant cost of having that MAC layer buffer. And in my example, it's like we have a 4-fold increase in age. So you want to minimize age or have information freshness, just remove that buffer. So just to conclude, so we considered age of information over wireless networks. So we considered single hop flows where source and destination are connected by link under general interference constraints. We considered two cases, active sources and buffered sources. In the active sources, the fresh information was always available at the source whenever a transmission opportunity arose. In this case, we obtained an peak age optimal and factor 2 average age optimal policy. In the buffered sources, we proposed a separation principal policy where we said that you design scheduling by pretending that all your sources are active, and you design rate control by pretending that there is a single link in the network, and that turns out to be very close to optimal. Some recent results. So in the active source case, we were not very happy with this factor 2 average age optimal, so we proposed 2 more policies, and this work appeared in MobiHoc and ISIT, for age-based and virtual queue-based policies, and they also utilize standard state information to minimize age. Last year in Allerton, we did similar policies for multi-hop networks under general interference constraint, and in SPOR, we have age minimization with alpha-like policies, and that's where ETA necessary. Thank you.